Hello. Hello, is there anybody? Is there anybody out there? Moshi moshi, konnichiwa, namaste, ciao. 日本語できます。我会说中文。De donde eres? Me tori hindi somos dahun. Bonjour. Je peux parler français aussi. Let's go. Let's have some peoples and let's play. Okay, I have only the last one in this level. Hurrah. Wait. One thing I forgot. So that tells me, for example, I think it's a face with a... I think I remember this one. It's like a clown and this... Wait. This is an eye. This eye is different from the other eye. And it's also slightly to the left here, instead of centered. So yeah, we can at least do some of this, right? How's everybody today? Konnichiwa. Don't be shy. Okay, 5 cannot be here. And... this is 2. Okay, cool. This has to be 9. 6, 7, 8, 9. Hello, hello, welcome, Sunbeast2. Thanks for the comment. So this game, it's called Picross, maybe in English. But anyway, so like here's a number 10. So that means there has to be 10 pixels in this column, which I did, which means that this has to be off. So I mark this like off. You don't have to mark, like, marking these as off doesn't matter. It's just for my own purposes. And then like down here is a 13, so there has to be 13 here. And the fact that this cannot be marked, or this cannot be a pixel, means that the 13 starts here. So I can fill these in actually. That will be 13 blocks. And I see that this column is 11, so it has to be going up like things. Like some of them have symmetry. This one almost has symmetry, but not quite. Like this 4 is different. And there's a 2 here instead of 1. But like, and that's not the center line either. So normally, if it had like horizontal symmetry, you would notice along this line. But that's sometimes important to notice. Symmetry can help a lot. So we got 1, 9, 1 here. So everything, that row is finished. This row has all 1s, so I can mark these squares next to the pixels. And same here. Same here. So like this is a 3, but I don't know if it's a 3 by having a pixel here or over here. So I can't really do that one yet. This is a 2 for sure. And we've got the 1 as well, so this is finished. 2. And we have the 1s here. Okay, what else? So here's 171. Hold on. How many empty tiles do we have? We have 11 empty tiles. So this has to be like this. 5, 6, 7. It has to be like that. Three block is in a superposition here. That's my fantasy way of thinking about it. So we have a 5 on top here, so this has to be 5. You can mark the 11 as finished. 4 has to be on the bottom here. And what else can we say here? That has to be a 1. Next is 6, so there's a 6 and a 1 in here. 2, 3, 4, 5, 6. Okay, it has to be like this. This is a 3. It's probably pretty confusing at first. But this is the best, definitely the best puzzle game I've ever played. By far. By far. Okay, this has to be 7. 3, 4, 5, 6. So these have to be filled in for sure. And mark that. There might be a little more I can do in here. I'm not sure. No, I don't think so. Alright, 3 1s. Which is the time here? Yeah, what's the time where you are? Where are you? What country? If you're in a country, maybe you're out at sea. Or on an airplane, perhaps. That would be a first on this channel. Could be on the South Pole. No, I don't know if they have good enough internet for watching live streams on the South Pole. Oh, well, in Antarctica, I should say, rather than South Pole. Okay, this one is finished, it looks like. Okay, which means this 7 we can now fill in here. 5, 6, 7. Cool. Information in this game tends to go in a, like, rectangular pattern. Like, you get some information here, and then it gives you information that goes horizontal, which now, like, I got this information that there's a block here, so I can work on this, and it often just goes around this. This looks like, oh, this looks like an Among Us character, huh? I'm sure it's not, though, because it's Nintendo. This is done. Oh, we have all these. Cool. And this is done. 13. Guess your country. My guess is Iran. Three, 4. Okay, I need. Need another 1 in this column, but I don't know where it is. These are all 1s here. In this column. There's a 4 in here, so 1, 1. So this is 4. And so kind of a goblin monster thing, huh? Which means there has to be 1 here. This is a 3. There has to be 1 here. Okay. So close. So close. Then I would guess Iraq or... I don't know, my geography's not that good. Based on that you said it's very late there, I was going for that area. No, I'm in Japan. Japan. Nippon. It's 10... And now it's 10:47 a.m. here. It's the morning. I'm in Toyama Prefecture. That's a 6. Okay, we got 3s we can do. And we have all the 1s done here. And 4 1s here also. One, 2, 3, 4? Wait, what? Oh, there has to be a 1 here. Okay. Then I'm gonna guess Turkey. That's not that close to Iran, is it? Oh, I guess that just before it came up on the chat. Oh, you're just waking up? Okay. You're talking about me, right? Yeah. Turkey, nice. We get some viewers from Turkey sometimes. Actually, that was my second guess after... I don't know why I guessed Iran. I guess because if I got it right, that'd be insane. But my next guess was probably Turkey. 1, 1. So 5 1s. 3. Oh, we got all the 1s here. If you're just joining in, feel free to say hi. 4 1s. We need a 1 here. We finished. Is it an astronaut? No. Some kind of machine. A slot machine, I think. Yeah, slot machine. Slot machine. You're just waking up? Okay. I thought you were, you said it was late, very late. What game is this and how do you play it? Welcome to the channel, thanks. Thanks for the comment. I'll show you. So, okay, the game is Picross. And... okay, so for example, okay, there's a 0 right here, right? It says 0, so that means none of these are pixels. And here's an 11. That's an 11, and that means there's 11 pixels, and they have to be connected. So it can't be here. Let's see. It's a little complicated to explain exactly how I know this, but these are filled in and this. A certain number of pixels have to be filled in if you work it out. Now there's a 13 over here. So actually, all of these, that's 13 pixels right there. And this has 12, so it's like that, except there's a slight wiggle room, which means I can fill these in, but I don't know if the pixel's here or if the pixel's here. Similarly, there's an 11 here, which means that's gonna be like that. But the 1 could be here or here, so I'm not sure about that. So there's a 1 and an 11, which means that there's 11 pixels, and then there's some separation, and then there's 1 pixel. So the 1 pixel, yeah, it can be here or here. I don't know yet. Does it kind of make sense? It's a little complicated. So, hold on. It's 4 a.m., so it's late. Yeah, I know what you mean. I know what you mean. I farted, huh? Sorry about that, guys. So loud, huh? I do that. Okay, 7. So these are not the easiest levels to understand. But there's 7 and 7 separated. So actually, it has to be... the block in the middle is empty with 7 pixels on either side. If you do the math, because there's 15 across, and 7 plus 7 is 14 plus a space in the middle. So it has to be like that. So I really love this puzzle game. Get to do math and stuff. It's not deeply complicated math, but it's not trivial. So this has to be 10 here. So 1, 2, 3, 4, 5. That's 10. Same thing here. Can't have 10 here, obviously, right? 5. 1, 2, 3, 4, 5. Okay. Somewhere we have a 9. I could probably do that. So hold on, let me think. 9 in the middle means these are definitely filled in. Same here, 9 in the middle. So I'll explain the math slightly here. So imagine this were 10. There's 15 across. If it were 10, definitely these are filled in. Because if it was 10 all the way to the left, this is still filled in. If it's 10 all the way to the right, it's still filled in. So you can kind of figure out what's filled in for sure by thinking, like, if it's one extreme or the other extreme, what is true for both of them. So this if it were 10, it would be just this, but it's 11, so I'm gonna add 1 on each side. 11 means that these must be filled in. Now I see that this is a pixel, so this has to be filled in here. And when I do that, I'm making a difference of 2 here, which means that these 2 blocks over here cannot be pixels. That's a little complicated, but it's pretty fun. Cool gem. Why is LOOL? Cool game, but why is it loud? Is that what you mean? Okay, you got it. Cool. Is it loud? Is that what you mean? Let me see the thing. I don't know. Okay, so this has to be connected. 1. Got 1s here. 1s, 2. This is a 4 over here, so at least I need another one here. LOD. I don't know what. Loud. Is it loud? Should I turn it down? The volume is loud. Is that what you're saying? Loud, by the way, is L-O-U-D. Is that what you're talking about? So we got threes. We've got threes here. Those are all threes. We got 4. So this is filled in, this horizontal one. We can do that. We got 1s here. That's a 2. And then this column is finished. Hurrah. And this column's finished. This game is so satisfying as you fill it out. So there's a 3 here, so I know that it's limited to this little area right here. 5 here, I can fill that in. And that's a 9 in the middle. 6, 7, 8, 9. Okay, this is a 3. And there has to be, I know where the 1 is now, so 1 definitely here. I think 6, 7, 8, 9. 8. This has to be 9, like that, and then there's 1 here. Why is no one typing? Oh, what's it called again? Hold on. Yeah, I mean, so a lot of people like to watch, just watch. That's totally fine. Lurkers, no problem. Yesterday I had 50, I think there's like 50 people watching it at some point, and almost nobody. I think there's 1 person typing for some reason, but that's fine. So it's called Picross. So let me see. I'll try to write it. I'm gonna bring up the browser. 1 second. Let me bring it up. Picross. I'm not sure I'm pronouncing it correctly, guys. It's Nintendo Switch. And so this kind of puzzle game was invented in Japan in 1987, which is the same year I was born. So sometimes they're just called Japanese puzzle games, or Japanese puzzles. And I mean, just this as a type, right? As a genre of puzzle game, as a type of puzzle game. They're also called nanograms for some reason. And there's also like an area of math related to this, because you'll notice it's very mathematical. There's actually some kind of deeper things you can try to study with symmetry and stuff like that. And as a field of math that's related to this is called tomography, discrete tomography. Yep. So this has to be 3 here on the left. Same here. And I have there's a game that is a 3D version of this, which I have. It's called Voxelgram. It's also, that's pretty cross-platform. You can get it on Steam. I'll write that in the chat for you guys. Hold on. You're good at math, huh? Tell me what a Lie algebra is. Okay, I'll give you an easy one. Explain modulo addition. Oh, that's not easy. You don't learn that in high school normally. What was I gonna search for? I was gonna type voxelgram for you guys. So the 3D version is voxelgram. That's the name of a specific game, which I've played before here. What, are you in high school? Because you're not going to know what a Lie algebra is. Don't know what that is. Yeah, most people don't. Even people who have a degree in math don't know what that is, which is unfortunate in my opinion, but that's the way it goes. Yes, I think you asked for a difficult question. Not necessarily, just a question. Quickly, without looking, just within a few seconds, what is 29 times 31? Can you do that? I can do it. It's pretty easy. If you know the trick, it's easy. There's a trick for multiplying that kind of number. All right, this looks like a harp or something. I'm not sure. Oh wait, no. You know what? This is probably a magnet. So I'm just based on intuition of the drawing, I'm gonna fill that 3 in. Yeah, I think this is a magnet, guys. 2. Okay. 4 over here. No, what? Okay, so the previously this was wrong. Okay, I made a mistake here. Guys, you didn't catch my mistake for me. I will make mistakes, I'm human. Have you taken calculus? Here's another question. Which of Euclid's... You chose to ask this to somebody who knows a lot of math. So, which of Euclid's 5 postulates are wrong? And why? That's another thing I didn't learn in school, but is quite interesting in my opinion. So we have another 1 up here. We got a 2 down here. This is finished. There's some... Sometimes you can use modular arithmetic in this. If you don't know, modular arithmetic is like if you do math on a clock, right? Because a clock goes back around. 13 hours goes back around to 1, right? And modular arithmetic, we use that a lot with programming. That's where I first learned about it. It's basically, you can also think of it as division. If you do division, like integer-based division, and then you have a remainder, the remainder is the modulo. Just fancy language for stuff that everybody kind of knows already. But that's especially important if you're going to work in different bases, like... Our normal number system is base 10, right? But with computers, sometimes you're using other bases. Base 16 is common because the computer is based in binary, which is base 2. So there's nothing special about base 10. They should actually teach that to everybody in school. The first time I worked with different bases actually was I was tutoring math, and I tutored someone who was in college and they were studying to be a teacher. And for some reason they made the teachers learn to work in different bases. And she was complaining. She's like, this is so useless. Nobody's ever going to use this. But I thought it's actually really good so that the teachers understand that there's different bases. And, you know, a student might ask, like, the question might come up. She needs to know, you know? Is you there? Whoa, you cool. Oh, did it pause? No. I'm here. Everything good on the stream, guys? That's a magnet. So, Sunbeast, tell me what's your favorite kind of math? What kind of math do you like? Beep, 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 beep. Anybody new to the chat? Say hi if you want to. I can explain how this game works if you'd like. I've got an 8 up here somewhere. So 16 and 8. I think, I'm guessing right away I can do that. Probably one more. Not sure. Yeah, I think that's right. 7, let me think. 7, I think I can fill this one. Not sure. I'm guessing I can fill it. Okay, 12. Adding and multiplying, okay. How high can you multiply? Like, do you know 12 times 12? Have you memorized it? And 13 times 13? I actually don't know 14 times 14 off the top of my head, but I know 15 times 15 is 225, 16 times 16 is 256. 14 times 14, is that like... No, I don't remember that one. You said your favorite math is addition and multiplication, so I was a little surprised. But that's fine. Why not? Beep 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 beep. What else can we do, guys? This has to be 7, so 1, 2, 3, 4. This is 10. Well, if you like addition, you're gonna love this game. There's a lot. I can do some algebra, nice. Algebra's nice, I enjoy algebra. I used to tutor math, guys, so I had to do a lot of algebra. Let's see, there's something here. I used to remember the math to do this quickly. But I'm guessing I have to have those in. What else can we say? That's 1, 2, 3, 4, 5, 6. Okay, this has to be 1. It cannot be connected here, because that would make 7. So this is definitely 1. Right here. By the way, I just noticed there's a 2 here. So you can fill that in. Force. So now I just used modular arithmetic in my head. Instead of counting out 12, I did this 4 plus here is 7. Modulo 5 is 2. So up to an error of 5, it matched, if that makes sense. My explanation is probably hard to understand, but instead of counting out 12, you can do some modular arithmetic. Okay, 6 here. X plus 5 equals 4. X is negative 1. So, what's your favorite math? My favorite math is some advanced math called Lie theory. That's what I asked you before. I asked you what a Lie algebra is. There are Lie groups and there's Lie algebras. And it's basically sort of the advanced study of symmetry. And it's very important in physics, actually. So that's definitely my favorite. But unfortunately, most people who have a degree in math, they haven't even really heard of it, which is sad. That saddens me, guys. 3, 5, something like that. I know I and E. I is the imaginary number equal to the square root of -1. E is called Napier's number. It's I always forget what it is exactly. Is it 2.4 or something, or 2.7 or something? But I use E all the time. I use E more than pi. Because in physics you use it, in advanced physics you use it all the time. E. And they use I as well. Though I is, that's an interesting question about I. I still don't know, is I the square root of -1, is it just a trick, a convenient trick? Because it's used all the time in physics because it's useful for rotation. And so, I mean, that's the basic reason. It's useful in rotation, so you can nicely package it up. Package up some rotation with the e to the whatever exponent. And physics advanced, well, I say advanced, I mean, once you get past, like, once you get into quantum mechanics, okay? You're gonna be using that all the time. Three point 3.14159265358979323 is as far as I know. 3.1415926. It's not 265. It's 26. 3.14159265358979323. So, do you know what I is, huh? Can you explain I to me? So there's a 1 and a 2, so it has to be 1 and then 2. So here's 2, but I don't know which way it goes yet. But looking vertically, I see that there's a 2 there, so we get sort of a flow of information. We've got the pixel here, so now I know this is a X, a batsu, and then we go 1, 2. So there's a 1, right? And this has to be 2. We got information flowing. 6. Sometimes you get stuck for a while, and then you get one little piece of information, and suddenly you get everything. So it looks like a radar dish, or radio telescope or something. I think this is the last pixel here. 3.14159265358979323. So I is the answer to x squared plus 1 equals 0. Yeah, nice. That's right. Good job. Have you been learning that in school, or you found that out with from searching yourself? I didn't learn about I until I was probably 14 or so. And by the way, that stuff with I, you can actually do it with, you can do the same stuff with matrix. So if I seems unreasonably confusing, just know that later on, you could switch everything to using matrices instead. Maybe not everything. I'm not. That's too much of a general statement. But for people who don't trust the whole concept of I and imaginary numbers, I would invite you to look at how to do it with matrices, or just ask me. I can always explain it in a video or something. I don't know why I put a 2 here. Oh yeah, it has to be. I wouldn't necessarily explain it on stream, but I can explain it at some point. So 11. Hello. 今日も今日 Picross, so this. Oh, you're doing matrices? Wow. Nice. Your brother taught you, okay. That's cool. Matrices were confusing at first for me. They don't really explain properly what vectors are. When you first are taught about vectors and matrices and all that, typically they don't really explain it properly, you know? So it's kind of tough. Even when I was tutoring it, I didn't understand it properly. I had to do a lot of study on my own. If I had gone to college and majored in a STEM field, then I would hopefully be properly taught, but I didn't do that. I was speaking Japanese. I speak Japanese. So this one's filled out. So that has to be 4, right? Okay, I could probably bet that... Yeah, this has to be 1, right? It can't be 2 and then 1. It has to be 1. And we have all the 1s in this column now? So, Sunbeast, do you know what a vector is? How many ones? I have 5. So 4. Oh man, why did I do that? Why did it do that? What do you mean? These are the columns up here. These are the rows here. And actually, I mean, this is a matrix, right? Basically, if you wanted to express this data as a matrix, you have a big... So this is 15 by 15. And you could just put ones and zeros in all of the entries of the matrix. Technically, they're elements of the matrix, but all the slots in the matrix, you just put ones and zeros to represent it. That would be convenient. Now, what you would do with that afterwards, I don't know, but maybe feed it into a computer. 1, 2 here. Were you maybe talking about... Hello. This is Pycross. I'll write it for you. Pycross. So matrix... So technically speaking, a matrix is just an array of numbers, but that doesn't tell you anything, right? But the reason the definition is so general is that matrices can also be used to store data. So like I just described here, how you could store this data in a matrix. But that's not the main use of matrices normally. The way that we use matrices normally is that matrices are used to transform vectors. So it's very important that you understand what a vector is, and then basically a matrix is used to transform it. So for example, in 2D space, so flat 2D space, just like we see on the screen here. For example, imagine a weather map, and if the weather person is pointing out, or it shows like wind speeds. Sometimes that's actually a vector field. You have little arrows all over the place showing wind speed. So each of those arrows is a vector. And a matrix could be used, for example, if you wanted to rotate all the vectors by whatever, 90 degrees, 10 degrees, whatever you want, you could use a matrix to rotate all of those vectors. Or you can use a matrix to scale the vectors, and some other kinds of transformations. So that's really the way matrices are normally used. Oh my god, no. The way that matrices are normally used is all about manipulating vectors. And I gave the... Oh, I'll catch up with the chat in a second. I gave the example of wind, a map with wind speeds everywhere. But technically in math class, we think of vectors where all the tails start at the origin, at the point 0, 0, 0, whatever. For technical reasons. So to explain those technical reasons, it would take much more time. If you really want to learn about vectors, you should look for videos on what is a vector space. You should learn what a vector space is. And actually 3 Blue 1 Brown has a really good series called Essence of Linear Algebra. So the subject of vectors and matrices is all that's called linear algebra. Let me catch up in the chat a bit here. So yeah, Pycross. Hello, I'm X Yellow, a fake of you Violet. Very funny. Oh, you like the Japanese style, huh? Me too. Thanks. Oh, I'm not talking to the mic. Sorry. I don't know if you could hear what I was saying. Yeah, House is Japanese. I like it too. For technical reasons, I'm leaving. Okay. All right. See ya then. 1, 2, 1, 1. This looks like a ruler and a... What's that one called? That's a triangular one? So I forgot to mention, like, I have a timer, right? And if I mess up, I lose time, so that's how the game works. Yeah, you're funny, Sunbeast. You want to play Roblox? Sometime. Are we friends on Roblox? I'm sort of, I have a kind of some memory of that coming back. No one can hear me, huh? Alright, so there's a 1, so it has to be 5 over here. This can't be... Yeah, this has to be 1. So these have to be the first ones. 3 has to go over here. And I think same for this row. I think this is the left 1, right? Yeah. And this is 3. It's the same thing. Middle 1, we got the middle 1. Zombies 2. What's chromophobia? Is that fear of colors? That's a game? What is that? One, two, three. So this has to be 4, right? Yeah. 5. Album by Tyler the Creator. I don't know Tyler the Creator. Can you play this single? I can't. I'm not playing music on the stream for copyright issues. Oh, you bought a shirt of it. Nice. I don't know Tyler the Creator. What kind of stuff does he do? Alright, so we got 9. So 3, 7, 8, 9. We got 2s over there. 2s. It looks like an electrical plug, huh? We got 1s. Have to be like this. Same right here, I think. Yeah. So this is maybe the electrical outlet here. Thing you plug into. All right. 4 1s. We got that. 4 1s and then 2 more. So it's gonna be like this. Oh, yeah. Can you help me with my chemistry? Oh, you have chemistry, huh? Lewis structures. Carbon, silicon, chlorine 2. Oh, I don't know. I'm not good with Lewis structures. I like to study about the electron orbitals. I find that quite interesting. But I don't know. I'm bad at basic chemistry. I guess I heard, though, the Lewis structures for O2 are often not represented in an accurate way, I guess. When you... Somebody was saying on YouTube, like... they feel like... In chemistry, you're basically lied to, and then you learn later why they lied to you about something. So you basically learn, like, a very approximate picture, and then gradually... you know, get more and more detail and more information, and learn that, okay, some of the story that they told you before isn't exactly accurate. And that's kind of... That's, maybe, probably just science in general. They have to do that. You have to learn the basic picture first. And it's always gonna have some... little... how to explain it? Window dressing. We got an 8 here, so I suspect it's the same, but we can do 13. I have a test tomorrow, huh? Okay. Well, is there somebody you can ask for help for Lewis structures? A bunch of 7s here. After this one, maybe I'll do the 3D. There's a 3D version of this game. Maybe I'll do that. I'm seeing a lot of symmetry. Is this fully symmetric? Yeah. This is fully symmetric. I'm pretty sure that means... Wait. do stuff like this. It's symmetric, so the bottom one has to be like this. No, I'm just kidding, but I'm gonna probably go watch a YouTube video on how to do it. Yeah, you'll figure it out. If you put in some effort and time, you'll figure it out. The stuff we're doing is so hard, it just doesn't really make sense to me. Try to imagine the molecules in 3D. You've got the electrons are in a cloud around the atom, around the nuclei. And of course the electrons, they repel each other. So if I had oxygen and oxygen, like the electrons are going to repel each other, but there's positive charge in the nuclei and negative charge outside. So of course they can sort of lock together in a way where negative charges are repelling, but the electrons, like the outer electrons of one oxygen, kind of get sucked in towards the other nucleus. So if you look at the electron orbitals, if you look those up, it's a bit confusing. And this is, by the way, this is not the best way to study for your test. But if you want to try to actually understand this stuff on a deeper level, there's I think there's 4 types of electron orbitals, but I think of them as 3 types. There's the spherically symmetric type. Of course, there's going to be that. You have that with just hydrogen, for example. Then, basically, the main type is where if you took balloons and tied them together, the balloons don't want to be like right next to each other. They kind of push away from each other. So you end up with like a tetrahedral shape, for example. This is almost a tetrahedron. Wait, let me see here. So you've got this is a bad example of a tetrahedron, but hopefully you know the shape. Anyway, if this were the nucleus, and you had 4 electrons, they would generally stick out in a tetrahedral shape. 1, 2, 3, and then 4 out on the top. That's exactly what would happen if you tied 4 balloons together. The exact same thing. So I think that would be like carbon. So, if I might make a mistake here, but carbon has 6 electrons. 2 of them are in the inner spherical orbit, and then so you've got 4 on the next energy shell, electron shell. So you have that tetrahedral shape. So I think that's why carbon forms like diamond, for example. Diamond is a very sturdy, strong material, right? because it has that energy shell with the tetrahedral shape, they can lock together in a grid. If you try to make if you try to stack spheres in 3 dimensions, like cannonballs, for example, you stack them in the normal way. Like you can try obvious ways to do it a few different ways, like in a square pattern, or a tetrahedral pattern, or a hexagonal pattern. And it turns out that those 3 are the same. You just look at it a different way, and you realize, oh, it's the same thing. So you can look up about that. It's sphere packing. Sphere packing in 3 dimensions. There's one lattice that is formed. And so that lattice, if you had carbon, that's a tetrahedron, and another carbon, which outside is a tetrahedron. Again, I might be getting details wrong here, so take everything with a little grain of salt. But this is, I'm not good at chemistry. But you have a tetrahedron, and you can start stacking them together like the cannonballs, and that will form that lattice. I think that's what diamond is like. That's why it's very hard, very difficult to penetrate that, because it's in some way it's optimized. It's the optimal sphere packing. Of course, there's going to be little tiny details that change things probably, but that's roughly the picture I have in my head. Yeah, you learned SPDF. Yeah. So S is the spherical, and then I get confused between PD and F, but I think of it as 3 types. There's spherically symmetric, then there's sort of the obvious stuff that would happen if you tied balloons together, and then there's a 3rd type that's very confusing looking, that you actually don't normally run into too much. And there's like hybrid orbitals as well. So oh, this is a Japanese food, onigiri. Probably this way, huh? It's a Japanese rice with the seaweed around it, onigiri. Let me see if I can just show what I'm talking about. Hold on. Let's see if I can show what I'm talking about here, guys. Whoa. I don't know what I'm doing, guys. Help! Alright. Let me get the computer screen thing up. Hold on. Okay. 1 second. One second, guys. I'm having technical problems. Hold on. All right. So we're talking about the electron orbitals. Right. So it is 4 categories SPDF. Okay. But what I'm saying, that's confusing. I prefer to think of it as 3 types. There's spherically symmetric. We see that with the S types. Then you have what I'm talking about with like balloon type, okay? Like here. Oh, it's not going to show. I want it to show it bigger, guys. Show it bigger. Please. See like this 4F? That's what I'm thinking, like balloon type. And then you have this weird type in here. How to explain the weird type? It's like if you had a hot dog and you put a ring on it. So that's, I think of it as 3 types. Now SPDF, I think that that matches more with like the periodic table and therefore the properties of atoms. But I'm just saying, if you're trying to think of atoms as these little building blocks that you sort of fit together, then my explanation is a bit easier to understand, I think. Also, let's find electron orbitals of carbon. I want to see if what I was talking about before makes any sense at all. 6 electrons, yeah. So we should have 4 other electrons, so... It's gonna be like that. Okay, maybe what I said is kind of nonsense. Sorry. I'm still learning. I've been studying some chemistry lately. Here's the tetrahedral shape I was talking about. There are some specific atoms where it gets interesting, like O2, how carbon works. Carbon dioxide looks particularly interesting. Yeah, I would like to find some good sort of intuitive stuff that relates with carbon specifically. That would be nice. Here, we got this stuff. We got a tetrahedron here. Tetrahedron! Spatial arrangement of orbitals in the carbon atom. I think this is what I was talking about, guys. Chat. No, not the picture. I want to see the paper. E-publication. Fabrication and characterization of macroscopic graphene layers on metallic substrates. Okay, so graphene is carbon, similar to diamond, but different structure. It's an allotope, right? Or rather, graphite. Graphene, yeah, both, right? Different allotopes. This is quite long, guys. This is like no, it's in Spanish or something. Whoopsies. here's English. Okay. I'm quite interested in this. Hold on. This I can do better here. Hold on. Hold on. Whoa. I'm big. So, yeah, carbon. Carbon presents allotropy, that's what it's talking about. So you have graphite, diamond, and amorphous carbon. Constituted by carbon atoms bonded by sp2, sp3, combinations of both hybridizations. So the hybridizations are going to happen because because all of this is quantum mechanical. You have superpositions, quantum superpositions. There exists another configuration of carbon, the polymer life form. It's found when carbon is diluted with hydrogen and presents low hardness, high transparency. Yeah. Because there's hydrocarbons, right? That are basically fats and stuff like that, polymers. But I don't know if I would call that an allotope, right? Because that's not just carbon, that's bonding with hydrogen. Anyway, the spatial distribution of polymeric carbon comprises a rich variety of shapes and lengths. Yeah, that's like the basis of organic chemistry. Hello, Mega Sharma. Good morning. How's it going? How's the weather in India? Gives rise to compounds with different chain types. Yeah, okay, we have aromatic, etc. Graphite shows a stable, trigonally bonded crystal structure. Oh, I need my coffee for this stuff. A guy was asking about this stuff and then he left, but now I'm stuck looking at this. I should probably make this bigger for people. Maybe. There we go. They're saying, okay, this, English is not their native language. They're saying trigonally bonded. I believe they should be saying tetrahedrally bonded. Figure 1.3. Oh, this is 1.2. Oh, wait. Yeah. Where's figure 1.3, guys? Chat. Okay, we have the 8 allotopes of carbon. I think this is fascinating. Carbon is amazing. So, I forget 8. Oh, okay. Wait. Which one were they talking about with graphite? Oh, they're not saying which one. Anyway, there's trigonally bonded. Graphite crystallizes in hexagonal, closely packed network. Yeah, like your pencil tip is graphite. And actually, you can, if you take your pencil and smear it on some paper, you can make single atom layers of graphite rather easily. If I recall correctly, a single atom layer of graphite will obscure about 14% of the light that passes through it, so you can learn to identify what looks like a single layer of graphite. And there's a way to make layers of graphite just using a pencil and tape. Pencil, tape, and paper, probably. That was developed a few years ago. Anyway. Okay, yeah, this is what I was talking about. Diamond structure results from the tetragonal. I would say tetrahedral, but I'm not a chemist. Tetragonal sigma bonding of carbon atoms and is only stable at high pressure and high temperature. It exists the highest elasticity module known to date. Diamond establishes the ultimate hardness limit. Anybody who's played Minecraft knows about this, basically due to the superior strength of its chemical bonds. Da 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 blah blah blah. Highest atom density among all solids. That's interesting. So you can chemically dope it, and there's some very interesting electronic properties. That's cool. I didn't know that. Diamond conventional preparation requires high pressure. Thin films of single crystal diamonds in thin film form are usually prepared by CVD method at high. I don't understand that. Furthermore, there's also a hexagonal diamond called lonsdaleite. Lonsdaleite. In nature, it forms when meteorites. Ooh, this sounds cool. Meteorites containing graphite strike the Earth. The great heat and stress of the impact transforms the graphite into diamond, but retains graphite's hexagonal crystal lattice. It is theoretically harder than conventional diamond, but is not demonstrated in practice. I bet it's hard to get a hold of that material, huh? It only happens when a special kind of meteor hits the Earth and the graphite turns into diamond. That's gotta be rare. I feel like I'm in real life Minecraft. Alright. DLC matrix? Diamond-like carbon. Okay. Diamond-like carbon and amorphous carbon. Besides diamond and graphite, carbon can form an amorphous phase. So I'm imagining that it's just sort of jumbled up. Amorphous carbon is obtained. So you might have a mix of these other. Let's look again at these things. So this is graphite, I'm pretty sure. It's hexagonal lattice. We've got like more exotic types. Like these are. I think this is a Buckminster fullerene, which doesn't really occur in nature, but we've built it in the lab. I'm imagining this is also a lab-based one. D, E, and F. This is a carbon nanotube, H. So G is probably the amorphous carbon. It's all just a jumbled mess, which means that locally it's probably mixing different aspects of these others, just in a jumbled mess. And then I'm not sure about A and C. Maybe that's supposed to be like the diamond. Oh, here we have the things. A is diamond. C is lonsdaleite. I think with diamond you could probably get more beautiful lattice structures. I think what they've put here is probably somewhat realistic, maybe. Because realistically, it's not going to be perfect structure. But I don't know. I don't know what I'm talking about. Yeah, we have the Buckminster fullerene and another type of fullerene. Another fullerene, so that's D, E, and F. These are not occurring in nature normally, I don't think. We've got the amorphous carbon is G, and single-walled carbon nanotube is H. So this stuff is pretty cool. And you can make you can make single layers of graphite, which that's called graphene, right? And you might be able to make carbon nanotubes. I don't think that's easy though, if you wanted to make them. Okay, but I think if you you set out to make them, you probably could figure it out if you look it up. So we're talking about the amorphous phase. Its close relationship with DLC, which was diamond-like carbon, is currently defined by whoever that is. Some kind of organization. Hard amorphous films with a significant fraction of sp3 hybridized carbon atoms. Okay, so the amorphous carbon is all mixed up, but if it has a lot of these sp3 hybridized carbon atoms, that's the diamond kind of structure. So if it has a lot of those, it becomes a diamond-like carbon film. Okay, cool. They can also contain a significant amount of hydrogen. Okay. These hard films can be fully amorphous or contain diamond crystallites. That sounds cool. Amorphous carbon is a carbon material without long-range crystalline order. Amorphous carbon is a carbon material without long-range crystalline order. Okay, so that's extra messed up. Just almost like not a liquid, but almost like one. It's like a liquid, but it's not actually moving around. It's stuck in place. So short range order exists, but with deviations of the interatomic distances and such or interbonding angles with respect to the graphite lattice as well as to the diamond lattice. I see. So it sounds like you have a mix of the... So fundamentally we only have the two allotropes of graphite and diamond appearing in nature. And then amorphous carbon will be locally it's going to have be a mixing of these two allotropes. That's why they talk about the graphite lattice and the diamond lattice. Actually, the suggested that hard amorphous carbon films and diamond-like carbon films are synonym expressions. From the structural point of view, the short order up to 6 to 10 atomic distances is synonymous of systems with nanocrystalline structure. Okay. The DLC matrix does not contain only one determined hybridization. Where's my coffee? Where's my coffee? Oh. Doing this today. Oh, you know what? I just realized the mic is far away, huh? You guys probably couldn't hear anything of what I was saying. Fail. Little things like that, we learn and we get better. All right. We got almost nobody watching, but I'm interested. I'm plugging along, guys. Blah, 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 blah. Actually, I'm starting to get tired. Microstructure is a system of covalently in a 3D network. Carbon is really important, so it's worth studying. Electronic band structure of graphene. Wow, that's cool. Dirac cones. What's a Dirac cone? That sounds awesome. Okay, I'll probably come back to this. Probably not on stream. But this is something that you should dabble in over the course of a few days. If I were really serious, I'd do a couple hours each day, 3 or 4 days, but I'm not that serious about it. Graphene-based quantum dots. This is a great little PDF, though. This is fantastic. It's huge as well. Some of this can inspire game design as well. But I'm a little curious why there's I think it was Spanish in the beginning. Yeah, okay, Barcelona. Okay, okay. So I think they had an intro in Spanish. Should I practice Spanish? I'm terrible at reading. Oh, wait. Yeah, this is too difficult. This isn't, wait, is this Catalan? Is this Catalan? I don't remember. I with the 2 dots? In Spanish, right? I see that twice now. But it's very similar to Spanish. This might be Catalan. Not sure. Scientific motivation. Maybe this is their master's thesis? What is a CVD reactor? I don't know. So he's saying thank you also to the group Fiman. something. I think this is I would like. And then also. Okay. I think he's also thanking his master students. Estudiants de master. And then we've got some names. Okay. This looks just like Spanish now. Aunque no haya tenido una influencia directa sobre este trabajo. Me gustaría dar las gracias de todo corazón también a Juan Garay, profesor que sin duda fue pieza clave en mi formación científica durante mis años del pavo y en el presente también a nivel personal. So, he's thanking his professor with all of his heart, who had was important in their scientific development. Creo que por fin empiezo a ver la luz. Parece que el cascarón ya se rompe. Anyway, not too sure. But this is definitely Spanish now. So I think he wrote in Catalan and then in Spanish. Para terminar y por ello, lo más importante, quería agradecer infinitamente. So he's still thanking people. So this is all just thank you. In Castellano, this is the other... Wait, what? This is another language, right? Castellano. So it's summary in Castellano. So we had summary... Well, these are thank yous. Okay. Castellano. That must be different from Catalan. Is Castellano? What does that mean? Not sure. What is castellano? Spangle. It's just Spanish. So I think castellano is just what Spanish people call Spanish, maybe? Where's the PDF again? Okay. Yeah, because this is Spanish. Okay. Okay, so it's summary in Spanish. El carbono es uno de los elementos más importantes en nuestra vida y el cuarto más abundante en la naturaleza. So, carbon is one of the most important elements in our life, and el cuarto, I think it's saying the most abundant element in nature, I think is what it's saying. No solo constituye uno de los elementos básicos. Okay, element is element. Elementos. So, el cuarto. Oh, is it the fourth most abundant? Maybe it's the fourth most abundant. That's probably it. That's probably it. Okay. So it's not only one of the most basic elements for life, but also is increasingly used in industry for the fabrication of materials, production of materials. The main characteristic of carbon is its capacity to create enlaces con otros elementos. So I think maybe bonds with other elements and molecules. And primarily thanks to its electronic configuration 1s2, 2s2, 2p2, en estado fundamental. So I was talking about an hour ago in the stream about the electron orbital structure of carbon, how it forms a tetrahedral, it can form a tetrahedral structure, and why that is. It feels like I'm hiding behind the mic, but why that is, what's the thing? Probably related to why you have diamond being the strongest thing out there, because it has this nice it's like an optimized sphere packing that you get from combining interlocking tetrahedra together, something like that. Can I move this? We'll try like that. Okay. Okay, por ejemplo, los bien conocidos hidrocarburos están formados por carbonos e hidrógenos, probably? Hidrógenos en cadenas o anillos. Not too sure about this sentence. Something about hydrocarbons. Están formados por carbonos. Hydrocarbons are formed with carbon and hydrogen. In cadenas, and anillos is a ring, so you can form hydrocarbons in rings. Those are usually aromatics. Right? This is organic chemistry, basic stuff in organic chemistry. I don't know what cadenas is. Al añadir radicales metilo, nitrógeno y oxígeno. I don't know if the G is pronounced like a G, like a G sound or J sound. Anyway, se da lugar a la formación de moléculas moléculas aún más complejas como ácidos alcohólicos. Yeah, so anyway, it's just really important in organic chemistry, of course. We've got the allotropes of carbon, like graphite, diamond, and amorphous carbon, and the DLC, which is we just saw, diamond-like carbon. But it's amorphous diamond that is like, amorphous carbon that's like diamond. Se han convertido en las variantes de carbono más importantes debido a sus propiedades físicas y a sus innumerables aplicaciones. Yeah. Carbon has... my brain is too lazy to translate it. El grafito comúnmente utilizado en las minas de los lápices. What is a lápiz? Is that a lattice? Las minas... Ah, that's a pencil, isn't it? Right? Is lápiz, is that a pencil? Yeah, graphite is un pencil lead. Es también utilizado por sus propiedades conductoras y como lubricante seco desde los inicios de la industria armamentística. The chemical properties are also important. Or sorry, not chemical, electric properties as a conductor. But I think you need to dope it. La unión de sus átomos se lleva a cabo mediante tres orbitales. En planos. Que diamante, por su parte, posee la mayor dureza hasta la fecha. The sp3 hybridization confers mechanical properties like hardness, más alto modulo, and the highest module of elasticity known. Tenemos también el carbono amorfo y el DLC. I love the DLC sounds like we're talking about video games. Downloadable content. So DLC has a low friction coefficient. Okay. Furthermore, debido a su triple hibridación de orbitales y dependiendo del cociente en los enlaces. Again, I don't know enlaces. Enlaces. It's just awkward to type with how things are set up right now. Okay. Links. Are they bonds? I think they're bonds. Okay. Alright, estas formas, three-dimensional forms of carbon. I'm gonna... Okay, now we're talking about sort of stuff they make in a lab. The buckyball, the fullerino. Fullerene? It's almost a tetrahedral shape, but it's different because it has 60 vertices. Did I say tetrahedral? Dodecahedral. The dodecahedron has 20 vertices. So it's not that. But it's like a big soccer ball, except it's not exactly that. Kind of looks like one. So that's cool. Actually, it's good for science. Yeah. It's good potentially for medicine. They think they might be able to put little drugs inside the buckyballs or something like that. Use it as a delivery device on a sort of nano level. Años más tarde, so some years later in 1991, they also discovered the carbon nanotube. So it has a cylindrical structure of carbon. One of the interesting properties. The interesting properties are the hardness and the electric conductivity. Depending on its I believe this is chirality. Not sure. But solamente... Okay, I'm getting a little tired of reading in Spanish, to be honest, but... how much more do we have? Ganbarimasu. I'm gonna keep doing my best. Where was I? Here. Solamente... I don't know this. Quedaba? Bidimensional allotrope. Some scientific theories can state that the two-dimensional crystals would be something unstable. So I think the theories were that something wouldn't work, but then in 2004, they were able to make it, maybe? I'm not sure. This paragraph is hard. Grafito pirolitico. What is that? I'm not choosing the easiest stuff to learn and to read in Spanish, guys, but I'm interested, so that's important. Una monocapa atómica de carbono. Yeah, this paragraph, sometimes you just gotta skip because you're just in over your head at some point. But I guess they won the Nobel Prize for this discovery. Not familiar with what this is about. Now we're talking about graphene. Oh, I think this is about graphene, maybe. This is... Okay, I believe this is what I was talking about before. About being able to get graphene from graphite. Maybe. So we got graphene and graphite. Now we're talking about graphene. So graphene is like... It's like graphite, but it's a single layer of carbon. As in one... It's a layer of one atom thick of carbon. Which results in special properties, of course. And it has a hexagonal lattice. So it's one of the allotropes of carbon. Lo que quiere decir que con una capa de grafeno podemos obtener de forma la-di-di-la-di-da. So I think from graphene you can make other forms, like you can build up other forms like graphite or nanotubes or fullerenes. They have sp2 bonds. The sp2 bonds are hybrid bonds. Which gives it 3 sigma bonds, 3 strong sigma bonds, and 8 weak pi bonds, I think is what it's saying. I don't remember. I've studied some chemistry just for fun, and I remember them talking about sigma bonds and pi bonds, but I don't really remember what it is. But we have it's a hexagonal lattice. So I can imagine where that you have 3 at each vertex on the lattice. You have like lines that come out in 3 directions. Those are probably the strong sigma bonds. I'm not too sure. So we have 8 pi bonds. I'm not sure about the 8 pi bonds. Okay, and some technical details. It's stronger than diamond. Harder than diamond. Wow. Cray cray. Could it just be that it's because the bonds are sort of very perfect? Like there's no, like normally diamond is going to have some contaminants. It's probably not going to have a perfect lattice structure normally. Maybe that's why. On the other hand, the pi bonds are responsible for these electronic properties. Okay, I don't know if we're going to read all these. Something about the electronic bands, valence, something. They intersect in one point. And then we have a Dirac point. That sounds cool. I don't know what that is. This is a bit over my head. But we have there's this thing called the quantum Hall effect, which is very interesting. Actually, that's something in quantum mechanics I don't really understand well at all. The quantum Hall effect is kind of tricky. There's a classical version and there's a quantum version. And we have ambipolarity. Never heard of that. Sounds interesting. So some kind of optical properties. Is this saying conductive paint? So okay. So we're talking about future, so big or great quantity of future applications. Que ya están aquí. I'm not sure if this is saying are already here or what that's saying. So structural materials, conductive paint, I think is what this is saying, which sounds cool. Graphene transistors. Wow. I didn't know that was a thing. So if you can have graphene transistors, it means you can build computers on graphene. Yeah. Assuming you might need a bit more, okay, to make certain kinds of circuits. Like for a computer, you typically need an on switch, for example. You typically need input and output. At some point, you're going to need storage. So you do need other things. But the most important thing in developing the computer was the invention of the transistor, which is basically an electronic switch, like an on-off switch. I don't know, capas. I've seen this word a few times here, but I don't know what it is. Conductoras transparentes, super batteries, and photovoltaic cells. That's basically solar. What a solar panel has. That's the part of the solar panel that gets energy from the sun, from sunlight, or any light. Photovoltaic modules. They're often called, I think. PVM, maybe. Si bien el primer método utilizado para obtener grafeno fue suficiente para que something. Okay, so this is the Nobel Prize they were talking about. So they're talking about, so they developed a way to get graphene just from rubbing a pencil on some paper and using tape to pull it off. And I think they got the Nobel Prize for that. It's an extremely simple method to get graphene. Best electronic properties. I'm not sure about this sentence. It's a little difficult for me. Let's see. I'm gonna skip to where I start understanding what they're talking about. Again, we have a transistor. Sounds to me like someone was able to build a transistor out of graphene using the method that we were talking about. So apart from the exfoliation, mechanical exfoliation, there exists also what is called the chemical exfoliation, where a solution of graphite allows for some kind of reactant or something. Again, we have kappas. We keep seeing that word. What could that mean? All right, we'll look this word up. Kappas. Layers. Okay, layers. That makes sense. Layers of graphene. The separation of layers of graphene, of existing graphene in the graphite that finally, I don't know, it's using ultrasound to get these layers of graphene out from the graphite. The result is, other than a large capacity for production, normalmente consta de grafeno oxidado y otras impurezas que obligan a una reducción del mismo, con un mínimo del 5% atómico de contenido en oxígeno. I don't know how to pronounce it. And so it sounds like you have a large amount of production, but you have some sort of contaminants, if you will, or impurities, where you have to, sort those out, I guess. Another method would be whatever the heck this is. Very technical sounding. Okay, anyway, these are methods of getting graphene. Graphene, yeah. Finally, another method in this thesis chemical vapor deposition, CVD. I think we saw this later in the paper, CVD. A hydrocarbon, like a gas precursor. Metallic, maybe? I'm not sure. I don't think that's metallic. Decomposed by temperature, pyrolysis. Catalyzed by a metal. En el que se depositan los átomos de carbono por precipitación o segregación, formando grafeno. So anyway, we're talking about a method to create graphene using CVD, chemical vapor deposition. This method appears tener el mayor compromiso entre calidad. So this method appears to have the best compromise between quality and scalability in the production of graphene. However, the major counterpoint, demerit, estriba en la aplicación de transferir el grafeno desde el metal. I'm not too sure about this. But there's something inconvenient about this method. I think that you have to get the metal, or sorry, the graphene ends up on top of this metal catalyzer. And you have to get it off, probably. Para la mayor parte de la caracterización y aplicaciones a un sustrato aislante como el sílico o polímeros. I don't know. So the objective of this thesis, superar las limitaciones actuales de las técnicas de crecimiento. I'm curious about this word. Let's look this word up. Wait, if I right click, wait. Emoji? I'm scared to click on that. Okay, crecimiento is growth. Crecimiento. Unas pocas micro? No, not micro. Excuse me. That's a mu. Micro. Wait. Yeah, micro, right? Micrometers squared. Tareas. Is that a task? I'll just check that. I think it's a task or something like that. Tasks, yeah. Okay, so let's see. The objective of this thesis is to overcome the actual limitations, technical limitations of the growth of graphene from a few micrometers squared. So that would be a very small unit of area, right? And extend the possible applications of graphene to systems that require, well, larger amounts, basically. Macroscopic amounts or something like that. So for this, different tasks have been realized. How many of these do we have? A, B, C, D, E, F. So I'm not sure if, I'm kind of curious if just reading all of this on YouTube is like it gets me in copyright trouble, but this is just available online, so it's really hard to imagine that, that I would be in copyright trouble just for reading this. Okay, I'm gonna briefly look at these things because this is getting pretty detailed. But we're growing graphene with the CVD method that we saw before. That's something vapor or something. Okay. This is pretty technical and precise, so we're going to kind of skip over it. B. Designing and constructing a new reactor in... Oh, this is also CVD. Graphman. They named the reactor Graphman. Incorpora los siguientes elementos. Incorporating the following elements. Is this like a magnetron head? Sputtering? Catalytic pulverization or something? I don't know, guys. This is crazy. We've got copper and nickel controlling the conditions. Anyway, that's pretty technical. They built some kind of new reactor. Cool. This is more CVD? I don't know. I don't know if I want to go too deep. Conclusions. Let's look at the conclusions a bit. The mechanical exfoliation is a simple process. And this word, I know this word in French. What do you say in English? I would just say convenient, I guess. Convenient for obtaining graphene. A single layer graphene. Okay. They talked about that. This is a conclusion of this summary. So since we read the summary, I don't think we need to care too much about what they're saying. I thought it was like conclusion of the results. En cuanto a la técnica CVD. So regarding the CVD technique, it is necessary. What are these? Superficie? I'm gonna look this word up. Surfaces. Okay. Good words. So for the CVD technique, pure surfaces are needed. Okay. If the initial copper, I think cobre was copper, maybe. Let's check that. Copper, yeah. If the initial copper is something or has defects, yeah, it's going to be a problem. You're going to have defects of graphene. Okie dokie. So the final layers, or the fine layers, I think, of copper silicon obtenidas mediante sputtering. I don't know what this stuff is about. Don't know. I don't know. It's coffee. Coffee time. Oh no, I'm out of coffee. Obleas de silicio. Okay, I'm gonna Google translate these two paragraphs because I'm curious what they say. I don't really understand them. Cheating. I'm cheating. Okay, these thin layers obtained by sputtering. Okay, mediante, this is like by or via. Okay, we've seen that a lot. Which are amorphous but thick enough to prevent diffusion and completeness, blah, 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 blah. Okay, I just want to look at this and see if I even care. For the carbon deposit directly on silicon wafer. Proved to be successful substrates. Okay. That's a big deal then. I don't know what Raman measurements are. Follow the presence of FLG in the diamond polished copper fragments. Peak D. Why is Google shoving everything to the side? Whatever. This is even hard to read in English. Anyway, this sounds cool. So what they're saying is that they have some good method for developing graphene. Las medidas Raman demonstrate the presence of FLG. So FLG, I think it's something layer graphene. Grafeno de unas pocas capas. So I don't know. Small layered graphene with just a few layers or something like that. But I thought graphene should have only one layer. And I think this paragraph's hard to understand, but this might be the real results of their research right here. So it could be really important. And this next paragraph as well. So I might end up coming back to those next time I study this. So this is probably substrate, substratos. In the substrates produced by sputtering, layers of copper of 600 nanometers with a barrier of 100 nanometers of nickel previously deposited. Oof. I don't know that word. It's getting really hard. How long is it? How much longer is this summary? Whew. Is this just a translation of everything I'm trying to read here? Yeah. They have the English. Why am I reading Spanish? Okay, it's a PhD. We're reading a PhD thesis. Okay. We've got the English right here. It's good exercise, though, for improving my Spanish. Different tasks. CVD method. Fabrication of graphene-based ultra-thin layers on metal substrates of large area and high quality by this modified CVD technique. Focusing on obtaining the material as effectively as possible. That's the goal, right? We want lots of graphene obtained efficiently. Characterization of the graphene obtained through different techniques in order to optimize their physical and surface properties, such as structural and morphological studies by Raman spectroscopy. So this is some kind of technique named after somebody named Raman. Da-dee-dee-da-dee-da. In this regard, I should say, we wanted... Actually, probably you need something different here. We wanted to take advantage of the engineering, explain in detail the technology of production of graphene by CVD, and other variants on metallic substrate to make fundamental progression of the graphene growth technology and in the comprehension of the control of the growth kinetics. Monolayer discontinuities to explore... This sentence is this one sentence? Oh, geez, guys. Maybe the Spanish was easier to understand with this sentence. That's. I don't know if I can even understand that sentence. Is that it? Wait. That's not a full translation of what they wrote. Is it? No, that's not a full translation of what they wrote. There's more information in the Spanish. the Spanish part here. Anyway, it sounds like they came up with a better way to make graphene. And that's exciting. So, good lord. Is there something in here that I can understand about their method? Introduction. Carbon materials retrospective. Ooh, this is long. What am I doing? I get sucked up into this. Anybody in the chat? Say hi if you're not too shy. Konnichiwa, genki desu ka? Bonjour. De donde eres? Ni hao. Maybe I should go back to playing video games. I need a break, I think. But this is cool. Carbon materials retrospective. I'm very excited to read that, actually. And here's this beautiful tetrahedral electron orbital. Love it. Yeah, it's tetrahedral. But we also have this shape. This is not tetrahedral. And so these are different kinds of different orbitals, right? We've got SP, SP2, and SP3. So SP3 is looking like a proper tetrahedron. SP looks like just a cube kind of structure. And SP2 is where you have this p orbital going up and down, and then you've got these SP2 orbitals that go out in a triangular pattern. Yeah. And so, because it's all quantum mechanical, you may have superpositions of these orbitals. That's why you have orbital hybridization. And I think I read this before a bit. Yeah, I was reading this before. So you can see the scroll bar. We're like 20% through. We read a lot of this stuff. Chapter 2, graphene and 2D crystals. Got this honeycomb structure of graphene. It's a hexagonal lattice, basically, but there's something weird going on that I don't understand. Because of the quantum mechanical nature, there's something going on with pi bonds and sigma bonds and the hybridization and all that I do not understand at all. So I definitely need to learn more about that. I don't need to, but I want to. So honeycomb structure is the base, and I'm not saying that they're not saying that here, but there has to be more quantum mechanical stuff going on. Which I guess if you learn about the hybridization, maybe if I wanted to learn it, I'd look online for orbital hybridization graphene. Graphene sheets can stack with three main different ways: hexagonal, Bernal, AB, and rhombohedral, ABC stacking. The differences between them are the coordination of the equivalent atoms of the different planes. Figure 2.2 shows the three types of stacking order. Notably, the interplane distance of approximately something is roughly the same in the three cases. Alright, so the AA stacking is just this hexagonal honeycomb on top of another hexagonal honeycomb. Then this looks... wait... this looks easier to understand than the AB stacking. But I think AB stacking... okay, AB stacking is where you have one hexagonal honeycomb with a vertex, like that's in the middle of the other, if that makes sense. It's like AA stacking, but you've moved one of the layers over so that the carbon atom is in the center, above or below the other hexagon from the other layer. Okay. Then we have ABC stacking. It looks similar to AB stacking. Not sure what the difference is, to be honest. Atoms of the graphene structure do not correspond to the points of a Bravais lattice. Indeed, the primitive cell contains not one but two atoms. Now keep in mind, they're translating in their head from Spanish, so some of the sentences can be hard to understand. Graphene structure, primitive vectors, reciprocal lattice. Anyway, this part of the paper is meant as a review for people who are, the intended audience is people who know chemistry quite well. So we can always look for more information. Hello. Oh, Koros, long time no see. How's it going? How you doing? It must be really early over there in Iran, right? How's it going? I'm good. Studying some... Actually, this is a paper about carbon. I have to use the restroom. Actually, it's really about a method of making graphene, but it has a lot of good information about structure of carbon. Carbon's really interesting, right? You've got these nanotubes. You've got, this is amorphous, which means it's all jumbled up. Of course, you've got diamond. You have graphite is B here. Graphite like you use in a pencil. In English, people call that lead, but it's not lead at all. It's graphite. 7 a.m. Okay. So I imagine you were up, you haven't gone to bed yet, huh? And then this structure that looks like a soccer ball, it's not exactly like a soccer ball, but it's similar, is a Buckminster fullerene, also just called a fullerene. These three structures in the middle, D, E, and F, are, they don't really occur in nature, although I imagine probably we would find it eventually somewhere, right? But I don't think we found it in nature, but they can be made in the lab. And all of these are just carbon bonds. No, I'm just studying for fun. I'm just interested. But I'm going to use the restroom. I'll be right back. Ah. I cannot study chemistry to save my life. So, but it's all right. I began by being interested in physics, right? Quantum mechanics. Quantum mechanics is crazy interesting. And I've studied a lot of other things like general relativity, unification physics, that kind of stuff, particle physics. And eventually, symmetry is really important. So if you study unification physics, symmetry ends up being really important. Specifically, something called Lie theory, Lie groups, Lie algebras. That's actually, those are extremely useful for understanding particle physics, the strong nuclear force and all that stuff. And so I've thought a lot about symmetry, and I'm actually, one of the reasons I'm interested in chemistry right now is from the standpoint of symmetry. And specifically, there's something called ADE. So ADE, there's many ways to say this, so I'll just throw out a bunch of different expressions, but these are types of symmetries. So I'll explain what it is, but it could be ADE type Dinkin diagrams, it could be ADE graphs, it could be ADE symmetries, that kind of stuff. So this ADE thing, what is that? Well, the A symmetry is basically, for example, a tetrahedron. So a tetrahedron, you have 4 vertices and they're all connected with each other. And a 2D version of that is just a triangle. But you can actually, and so 3D version is a tetrahedron. You can go into higher dimensions, and that is called a simplex. So you could have an n-dimensional simplex. So to try to imagine that, start with a tetrahedron, just so we're all on the same on the same page. Let me bring up a tetrahedron, I know some people don't know what it is, so we'll just bring it up. So tetrahedron is this shape, okay? It's one of the Platonic solids. It's a regular polyhedron. All of the faces are identical to all the other faces. All of the vertices are identical to the other vertices. All the edges are the same as all the other edges, blah, blah, blah. So you can rotate it in different ways, and you have symmetry. And you also have a group in math. If you study symmetry, if you study symmetry in math, like you can study it at sort of like a middle school level or high school level or whatever, just basic symmetry, right? But in a more advanced sense, there's group theory. So group theory is the study of groups. And a group has a definition. It's not that hard to learn about it. Now you're in college, but I think you started college recently, right? I'm not sure if you'll study group theory. I think you're studying to be a doctor, is that right? I have kind of a bad memory, so let me know if that's right or not. But if you're studying to be a doctor, I would guess you're not going to study group theory, probably. But if you were studying to be an engineer, you might. I'm not sure if engineers study group theory. Maybe. If you take an abstract algebra course, part of it is group theory. Yeah, and year 1 and year in. But I would suspect, I don't think doctors study group theory, to be honest. But anyway, it's just, an example of a group is all the kinds of rotations you could do to this tetrahedron so that it returns to its original position. Same thing with a cube, right? Here's these are the 5 Platonic solids. We have the tetrahedron, this is an octahedron, this is a cube, we've got the dodecahedron, and this is the icosahedron. So we can study these and say, how many different ways can you rotate this object so that it returns to the initial configuration? So for example, the dodecahedron, if I choose a vertex, well, there's 20 vertices on the dodecahedron. So I can rotate it in a way to go to any of the other 19 vertices. But I can also, you see that each vertex has 3 edges coming out from it. So I can rotate different ways to match it like that. So I could keep the vertex fixed, but I could rotate around basically in a triangular configuration. So the dodecahedron has its group structure. It'll have a subgroup that is similar to sort of a triangular symmetry. There's definitely a triangular symmetry in the dodecahedron because we have these 3 edges coming out. And you can look for more technical details, like if you type in Google dodecahedron group, it should come up. So it'll definitely have some kind of triangular subgroup. We haven't studied it. I haven't seen it in the charts. I'm not sure. Correct me if I'm wrong, but I think the algorithms for Rubik's cubes. Exactly. A Rubik's cube has a group structure. It is a group. And it's very important for a group. It's very important that, the identity is very important. So the identity just means do nothing. I actually have a Rubik's cube here. Hold on. I have 2 of these. This one's a little simpler to talk about, and it's solved, so that's nice. So if I do nothing, that's the identity. Then we can talk about rotation. So I haven't studied in depth the groups behind this. But I would start by, if I were trying to study it on my own, of course you can look online. That's easy, but sometimes it's rewarding to try to figure things out as much as possible by yourself, right? It takes me like 10 minutes, at least like 10 minutes to solve a Rubik's Cube. I'm not very fast. Yeah. Do you have a record? But when I did the Rubik's Cube, I did not look online how to solve it. So I spent a few days studying on my own. Which I don't know if that's a waste of time or not, but it can be more interesting sometimes to do things on your own. You might learn something by doing it that way. 15 seconds? Whoa, we got a pro. You're a pro. That's super fast. Dang. Wow. So yeah, so every action you do on a Rubik's Cube is some rotation, right? So you have 6 faces. So you have 6 ways you can rotate. Well, you can rotate clockwise or counterclockwise, but let's just call that one thing, because you can rotate it 1, 2, 3, 4 ways, including the identity. So we'll call the identity as a separate thing. Identity is just doing nothing. So we have 3 ways to rotate a face, and we have 6 faces. So I suspect you're going to have 18 operations plus the identity. There might be some overlap there. I don't think so, though. I'm guessing you have, with the identity, I'm guessing you have 19 operations on either of these, actually. It'll be the same thing here. So what you do if you want to study the group structure is you write out the operations, and then you compose them. So you look at, okay, if I do, you have to label them. So I do this operation, and then I do this other operation. I get a new state, basically. Hello, Scotch. Hi, how's it going? And this also, this is, what we're talking about here is discrete group theory, meaning it's not continuous, right? So if we were talking about a sphere, you can rotate a sphere continuously, right? That's not just discrete. So if you want to study sort of continuous group theory, that's what Lie theory is all about. You have these things called Lie groups. And those are super important in physics. Okay, you gotta go. All right. Thanks for saying hi. Thanks for hanging out. And so but I'll just keep talking about whatever. So these also have a dual. I can actually explain some of this in Blender. Hold on. Here's Blender. Bring up Blender and talk about these platonic solids. That's a cube, obviously. We get to start with a cube. I'll just get rid of the camera and the light. So in Blender, I can make some of the more complicated ones. Let's make a tetrahedron. You can make a tetrahedron from a cube. So I can connect some of these vertices like this. So I have a triangle, so I'm almost done with the tetrahedron. I need one more point. Now, if I use this point, the problem is that the edges are not the same length. If I had like this edge and this edge, they're different lengths. What I actually do to make the tetrahedron in a cube, I use this opposite vertex. So you see that's opposite of the triangle. I'm going to connect these like this. And now I'm going to, just to finish the job, I'm going to get rid of a lot of the extra stuff here. Actually, whoa. I should get rid of all of the faces if I can. Yeah, okay. And now I'll make new faces. And we have a tetrahedron. This is actually a tetrahedron. My problem is this tetrahedron is oriented in a slightly weird way. So I'd like to figure out how to make it, to easily make it in a way where it's like, I don't know, just sticking straight up or something more obvious. And if some of you are interested in Blender, the other step I would do here is to click, where was it? Here, to click here and click on face orientation. Okay, this shows us that I did this correctly because the inside here is red. These are the inside faces, so it matters for the normals, that the normals are pointing the right way. If I had made the faces in some different order, it would be red, and I would need to fix it. And you can just I think you can go to mesh, and actually I can press F3 and flip normals. Yeah, here, Alt N I guess it is. But I don't really want that, so I'll do it twice, and there we go, flipping the normals. So that's a tetrahedron. We can also make, well, the cube is super, you start with a cube, that's not a problem. Let's make so the icosahedron is easy. You make a mesh, an icosphere, and then you just click here and you make it one subdivision. We've got an icosahedron. And the dodecahedron is the dual. So I wanted to explain the dual thing. Which actually, it's easier to explain it with a cube. So let's make a cube. And then to make the dual, what I can do is Control B for, oh, sorry, not Control B. Wait, what? Uh-oh. Okay, anyway, it's bevel. Bevel. And wait. Bevel should be Control B. I think I can also get it by going to Here. Bevel. Okay, now I can adjust it. So this is a bevel. Whoa, it's doing it twice. No. All right, so the bevel, if you look at the vertex, it's going to start cutting it down, basically. You see how it cuts it down? This is truncating. And I can truncate. Whoa, so it goes like this, which is kind of cool. We go back to a cube. But okay, so if I truncate until these things meet each other, like this, then we have an octahedron. And in Blender, I can go a little too far, and then I can go down here, and I can do clamp overlap. And this is an octahedron. So the octahedron is the dual of the cube. And so there's at least a couple ways to go from an object to its dual. I've shown you through truncation. We could have also, you can see there's 6 vertices here. Those correspond to the 6 faces of the cube. I could have just made vertices inside, in the center of all the faces, and then connected them. That's another way to make the dual. And so for the tetrahedron, if I do the dual of the tetrahedron, I get another tetrahedron. And then the icosahedron and the dodecahedron are duals of each other. So I'm going to use that fact to make a dodecahedron. Let's do that. So we start with an icosahedron. We go to icosphere, make sure it's on 1 subdivision. This is an icosahedron. And then I'm going to bevel in order to make the dual. Where's my bevel tool? Here it is. So I'm going to bevel, and we're going to... So actually, if there's some point here where you actually have... Is it a soccer ball? Yeah, the truncated icosahedron is a soccer ball. Maybe like this. I think, is that right? I could be wrong. Anyway, we truncate until it matches. That's a dodecahedron, but I'm going to go slightly over, and then I'm just going to clamp the overlap. One thing I forgot to mention, right now, if you watch carefully, where the vertices are coming together in a triangle, we have 3 vertices coming together. So when we do this, we're going to have too many vertices in each spot. So we can go to mesh, clean up, and merge by distance. This will get rid of the extra vertices. It says it removed 40 vertices. That's because the icosahedron has 60 vertices, while the dodecahedron has 20. So we got rid of 40 of the extra vertices. When you do the truncation step, it's not removing vertices, right? So anyway, this is a dodecahedron. Okay, anyway, so what I was talking about earlier is that if you study symmetries at a very advanced level, and by advanced, I mean not... So we're talking about Lie theory and ADE symmetry. A lot of math PhDs don't even know about this. Okay? So I'm just saying that so that people aren't disappointed if they go to get a degree in math and they never study this stuff. But if you study symmetries at a very deep level, the ADE symmetries are very fundamental. You can kind of construct other symmetries through ADE. And the A symmetry is the tetrahedral symmetry. It's actually the whole infinite family of n-dimensional tetrahedra. They're called, when you talk about them n-dimensionally, they're called simplices. So the family of n-dimensional simplices, that's the asymmetry, which just means, like, if you look at the tetrahedron, you have 4 vertices, and they're all connected by edges. So in my head, this is sort of like permutations. If you give me some number of objects, like you give me six or 7 objects, and I imagine that I can permute, I can talk about all the permutations. One way that you can develop all the permutations, so in case somebody doesn't know, permutations are just reordering things, okay? So if I have 7 people and I want to figure out how many different ways can I order them, like let's say we have a tournament and they're all going to be rated, first place, second place, third place, and so on. How many different possible outcomes are there, right? Those are permutations. So you can generate all of the possible permutations by lining things up and then allowing yourself to swap neighboring ones. And that's a useful thing to know if you're doing programming or computer science. Okay, so I'll explain some of the technical stuff. So a permutation group is called a symmetric group. Hey, what's up? How is it played? Oh, yeah. I forgot about the title here. I was playing a game earlier, a puzzle game. And, hey, Enzo, how are you doing? Long time no see. I was playing a puzzle game, and I figured most of the audience won't understand how it's played, so I figured I'd put that in the title. But that's no longer here nor there. So, okay, so the permutation group. I wish they'd just call it a permutation group because it'd be easier to understand. But in group theory, it's called the symmetric group. So that is the group that has all the possible permutations. So permutations are just reorderings. And these symmetric groups, and that terminology is also confusing because when people like me are trying to explain group theory to the rest of the world, we sometimes say symmetry groups. And I've even seen this, I think, in papers. And the reason we say symmetry groups is just to remind people that we're talking about symmetry. But symmetry group doesn't really mean anything. That's just a redundant term. That's either sort of technically wrong or people are just trying to make it easier to understand. But symmetric group specifically is referring to a permutation group. So all the possible permutations of a set of objects. Which is kind of related to the Rubik's Cube because you can take the possible transformations, so all the things you can do on the Rubik's Cube, like rotating some face. You can take that and then talk about all the permutations, all the possible permutations. Anyway, so it's there's a theorem in group theory that's really important, which says that all groups are subgroups of some symmetric group. So what that means is that the symmetric groups, which are the set of all permutations of some number of objects, those groups are like the big daddies of group theory. Okay, so the symmetric groups are the big daddies, and all groups are subgroups of the big daddy symmetric groups, the permutation groups. So the permutation groups, that's not the technical term, they're called symmetric groups. Those are super important in group theory. Okay, and the A-type symmetry, which is the symmetry of the tetrahedron or the n-dimensional simplex, in my mind, I think of permutations because if you give me 6 people and you say, what are all the possible permutations? I can write 6 dots on a piece of paper and I connect all the dots. Each edge is represented by a swap. Or sorry, if I'm swapping 2 people, that's sort of corresponds to an edge. So I'm being hand wavy and not rigorous, and maybe I should sit down one day and think about how this actually could be rigorously explained. That'd be a good exercise for me. But in my head, there's some kind of map between the symmetric group, some kind of set of all permutations, and each object is represented by a dot, and then you just connect all the possible edges between the dots. There's some kind of correspondence here. I'm sorry, it's a bit hand-wavy. But there's got to be some kind of connection between these n-dimensional simplices and the symmetric groups, permutations. Anyway, so that's the A-type symmetry. It's the And for those who are just tuning in right now, the n-dimensional simplices, okay, that's basically the tetrahedron is a, here's the tetrahedron. That is the three-dimensional, that's the 3-simplex, okay? So the 4-simplex, it would be the 4-dimensional analog of the tetrahedron. And you can kind of imagine it. So you start with the tetrahedron, make a point in space, and then connect that point with the other edges. And then imagine that you can kind of move. So if you're trying to imagine 4 dimensions, one trick is start with 3 dimensions. So we have a 3-dimensional tetrahedron, for example. And then we try to make like a movie, right? Because you can consider time as a 4th dimension, right? So you can make this movie in your head where this tetrahedron is one cell. If you have a 4-dimensional object, we call that a, okay, it's a lot of terminology. But if you're talking about n dimensions, we talk about polytopes. In 3 dimensions, it's a polyhedron. N dimensions is a polytope. And actually 4-dimensional has a special word. I believe it's a polychroma, maybe? Anyway, it doesn't matter. So in 4 dimensions, so in 3 dimensions, the solid is surrounded by faces, right? But in 4 dimensions, this solid, the polytope, is surrounded by cells. And those cells are each of those cells are themselves typically polyhedra. So just like a cube is surrounded by 6 squares, right? A 4-dimensional hypercube is surrounded by, I believe, 8 cubes. So we call those cubes that surround it, we call those cells. So you can imagine, if you're trying to imagine a 4-simplex, okay, the 4-dimensional analog of a tetrahedron, what you're going to do is you have this tetrahedron, and then you imagine that as one of the it's one of the cells of the 4-simplex. And so you have this tetrahedron, you put a dot in space, and that's your 5th vertex. And then you make a movie in your mind where the movie transforms this tetrahedron into a point. I might be able to actually make this. Okay, so let's delete this. I wish I had a faster way to make a tetrahedron. The only way I know is to start with a cube. So let's try to make what I'm talking about here. Okay, so what an awkward positioning for the everything is so awkwardly positioned right now on my desk. Okay, I explained this process like 20 minutes ago in the stream, but I'm making a tetrahedron from the cube. And again, if I used these, if I then used this vertex to try to make a tetrahedron, this is not a regular tetrahedron because the edges would be different lengths. This edge is a different length from this edge, so that's wrong. So what we're going to do is I'm going to use the opposite vertex here, and I'm going to connect. So we have the triangle we already made, triangle. So what I do is I pick a vertex and then I make a triangle around it using the vertices of the cube. Now we have our triangle, and then you have to choose the opposite vertex. And you connect these. And then I'm going to delete all the faces. No, not. Delete the faces. We have this. And then we just connect these. But maybe I'm happy like this. Oh, we can always use wireframe mode. Let's just connect these. Back to solids. I'm missing a face. Here's a face. Let me just see if I need to invert the normals. Hold on. Face orientation. Okay, it's blue, so we're fine. We don't need to invert the normals. Okay. I'm trying to explain how to try to imagine a 4-simplex, which is the 4-dimensional analog of the tetrahedron. So here we have a tetrahedron. So what I'll do is I'll make a point somewhere in space. So can I just add a vertex? Oh, I'm going to add a vertex somewhere. So I'm adding a point in space. So the way I'm going to do that, I'm just going to take a vertex and extrude. Okay. And I'm just going to delete this edge. Delete edge. Deleted the vertex as well. I don't want that. Why are you deleting? Anyway, pretend this edge is not here. I just want a point in space. And let's make it. Yeah. So what you have to do. I've never tried to do this demonstration before. So you have to imagine a movie where the tetrahedron gets smaller as you go through it. Until it collapses into this point. I'm not sophisticated enough in Blender that I can actually demonstrate this. Let me okay. Let me get rid of this vertex, and then I'll use a separate object. So I'm gonna add. Let's add a cube, and then just really scale it down. Okay, this is our point in space. And then you imagine a movie where it's collapsing into the point. So it will both move towards the point and it will collapse at the same time. This will allow you to make a movie in your head that is similar to if you took a triangle, took one of the faces of this tetrahedron and then collapsed it. You did this, the 3-dimensional analog of what we're talking about. So like, for example, I'm moving, here's a face, and I'm moving it to this point, the opposite point. I'm moving it there, and I'm collapsing it. And it will just, you're just sort of, you've taken a cross-section, and then it's like you're moving through cross-sections of the tetrahedron. So there's an exercise you can do that's trying to do the same thing, but in 4 dimensions, and blah, 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 blah. It's a little complicated. But it's a good exercise. And so it would, if you do this exercise, you can try to understand the 4-dimensional, the 4-simplex, which is the 4-dimensional analog of the tetrahedron. So that's the asymmetry. The asymmetry is the n-dimensional, the n-simplices, okay? The d-symmetry is the symmetry of the n-dimensional hypercubes. So in 3 dimensions we have a cube, in 2 dimensions we have a square, in 4 dimensions we have a 4-dimensional hypercube, sometimes called a tesseract. I think a lot of people have seen images of the tesseract. And I think it's called the tesseract by science fiction. It was called that by science fiction writers in the beginning, maybe. But I think it's somewhat ordinary now. But these are, we can't really show 4-dimensional shapes, right? So we try to represent it basically by making a projection. So if you need help understanding that, the projection is, it's basically a shadow. If you shine light, here's a projection, right? So the D symmetry is the n-dimensional hypercubes, and then the E symmetry in some way corresponds to the symmetry of the dodecahedron and the icosahedron. But I don't fully understand it. I'm on a mission to understand it. the E symmetry, which also is E8. Some people may have heard of E8, which is, there's a unification theory of physics using E8. Yep. So that's a bunch of random physics information. Whoa! Mike fell. I'm sorry. I'm gonna go back to playing silly puzzle games, unless somebody has any questions. Somebody was asking about chemistry, and we went on a long journey. Let me switch back to the Switch. Switch, where are you? Go like this. Huh? Oh, I moved it somewhere. No. Well, that doesn't matter, actually. Oh. Oh. There we go. Now if somebody wants to know how it's played, we can actually do that now. This is the best puzzle game ever created. Known fact. Oh, that was lucky. That was a mistake, but it got lucky. Oh. So I lose time if I mess up. And eventually, so if you mess up too much, you run out of time. And yeah. So this, the number 0 here means that this column has 0 pixels. The number 8 means there's 8 pixels, and then there's a space, and then there's 3 pixels in this column. Same thing for the rows. So I know there's a 1, but I don't know which one I've found. So 5 and 7, I got this on this row. You don't have to mark these, but it helps organize your thoughts, I guess. We got everything in this row already. We've got the 1 here. This is a 3, so I can fill in these pixels. One, 5. Beep, beep, beep. We have 3. Okay, this has to be like this because of the row. There's a 4 here, so... And you have to go, when the song has that part, you have to go, hee-haw. That's another important part of the game. If you don't, very bad things will happen. Nobody wants to find out what actually happens if you don't do that. It's very important. We got 4 here, so we can mark these. So we got 3 in this row. It can't possibly be here. At least this has to be filled in. 3. This has to be 3. I think that's gonna be 3, right? Yeah. So these have to be 2. There's also a 3D version of this game. Alright, we need a 1 here. Yay, it's 2 people. I think it's... Is this gonna be mother and father or something? Or grandma and grandpa? Kokeshi? I don't know that word. Kokeshi? Don't know what that is. Kokeshi. 何ですか? Kokeshi. Okay, we have 11 in this row. Ignoring this part, we know it at least has to have these filled in. Since I know these don't have pixels, I can add 2 over here. Seven, 8. Wait, what? Okay, 10, 11. Okay. Two and 11 is 13, plus the gap is 14. I think it's gonna be 1, 2, 3 like this. I'm gonna bet on it. Nine. Do we have symmetry? It looks symmetrical. Seven. It's 9, right? It's a key. No, it's a bottle opener. Sennuki. That's a bottle opener. Sennuki. Beep 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 beep. This mic is at a weird angle, huh? Sort of weird. Oh well. Pa. That's a little better. This is weird stuff going on back there, huh? 13 here. Pepper. Beep 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 beep. 6 in the column. Got 2 here. Is this Australia or something? Nine and 1. Probably this is filled in, so it has to be. Which means 1 is here. 7, okay. Six. Six, 7, 8. Beep 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 dee dee. Beep beep beep. So that's 6. Alright, we're getting information. This row has no information, doesn't change anything. 9? Wait, it has to be filled in, huh? The flow of information. Flows. Information flows. Like quantum mechanics, huh? Maybe? Alright. think we're looking at Australia. One more block. Here. Australia. Australia. Beep, beep, beep. 3, 4, 5, 6. Beep, beep. One, 2, 3, 4, 5, 6. 14, huh? And 2. That's gotta be filled in, right? 13, 14. Yeah, it's filled in. Okay. 2, gap, everything. Beep, 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 dee, dee, dee. All ones. We need one more 1. 3 and then 1s. Okay, this is there. Is this a sewing machine? 4. 1, 3. This has to be 3. No, 2. It's 2 and then 3. Okay. We got 11 and 1. Same. 1, 3, 2. This has to be 1, so we can fill that. Okay. 1, 3. 3, 4, 2. They get a lot harder later. Right now, it's still pretty straightforward. You just do what you can for a row, or for all the rows, do what you can for all the columns, and keep switching back and forth. Gotta sometimes notice if there's symmetry, especially horizontal symmetry. 3, 3, 1. End. Is that a sewing machine? Machine. It just says machine, but I think that's a sewing machine. So 3 and 1, that'll be filled in. Or 13 and 1, I mean. We got 5 here, so... $12 and 2 will be filled in. 15. 13. This is just 4, so... Yeah. No. 8 and then 2. Alright, this will be filled in 4, 7, 1, 9. I don't know what the best angle is. It's like a beaker, huh? Flask. Frasco. 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 Flask. We're learning Japanese as we go. Alright, 6, 3, 2, that's gonna be 5, 11 plus 2 gaps, 13. 13, huh? That 1, 2, 3, probably. The math is interesting. Do we have symmetry? Yeah, we have symmetry. Okay, that makes things a lot easier. So symmetry, so this has to be like this. Taishōsei ga arimasu. Yoko no taishōsei. C'est symétrique. Voilà. Alright, these are twos. What else can we say? What else can we do? Alright, we got 3. A star, a medal? Medaru? Kunsho? Is that a medal? It must be. Kunsho. Medal with a D. M-E-D-A-L. Okay, no symmetry. 15 at the bottom. Ten, 13. This will be filled in. Beep beep beep. All right. 7, 11, 12, 13. advanced calculus. So we got a 1 and a 4 in here. That's 6. Takes up 6 thingies. So it's gonna be filled in. We got a 4 in this here. And here. Beep, beep, beep. What else can be said? These are 1s. That's a 5. That doesn't help. Wait. 8, 9, 10, 11. No. That's a 3, obviously, so... Okay. This row is complete. Or column, rather. Column is complete. Does that help? Obviously there's not a 3 here, so we can do that. That's a 5. That's going to be a big help. That's a 4. We have 4 and 2 over here. 7. Got 4 here. This row is 3, 3, okay. 1 and 7, okay, this is another big help. So 1, 2, 3, 4. Okay. Seven is finished, right? 7. That pushes this one over. One, 3. row is complete. I think maybe that was a mistake that I did that. I mean, it works, but I think I got lucky. Maybe. 3. Do we have all of them there? What else have we got? Oh, this thing got bumped, huh? It does that. Beep, 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 beep. Que tarea. What a task. Yes. I think one more block, maybe. Probably here. It's a medical it's an ambulance. Are the top parts like sound coming out? Or is it a no, it's not a helicopter. Is it a helicopter? Might be a helicopter. But what? It has wheels, no. That represents sound coming out, huh? At the top. Yeah. QQ shot. Ambulance. QQ shot. We beat a level. Congratulations, おめでとうございます。レベル3の問題はすべてクリアされました。さあ、次のレベルに挑戦してください。Thanks, Mario. Should I go Wario? Dun, 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 dun. So with Wario's things, it doesn't tell you when you get it wrong. You have to go all the way to the end without getting it wrong. 間違えたら教えてくれない。最後までになんか、まあ、途中で間違えてもいいんですけど、まあそれ直して最後に完成できたらそれで OK。そういうモードです。ピッピッピッピッ。この音楽大好き。I love this music. Oh, caffeine. Get me some caffeine. Alright, 11 plus 4. 1, 2, 3, 4. Can actually fill it in. So if you make a little mistake, it will often cascade, and you will not be happy. Mistakes are bad. Yes. Mistakes bad. Can I say more about this? We can block off these 3. This row is 5, so these are no-nos. Those are batsu. X. Batsu. 12. 12 and then 1. And this has to be like this. I could have filled in the 5 here. a lot sooner. And we have 9 here as well. This makes it a little easier, folks. What is this thing, by the way? It looks like an amoeba or something. 5, 1, 1. I could have filled this in from the beginning. Okay. Is this like a talking bubble with the ... in it? 1 and 12. 5. One, 11, 1. Got it. What is that? The heck is that? Okonomiyaki? Wait. Orionza. It's the it's a constellation of Orion. Orionza. Okie dokie. Why not? They can do that. Anything is possible. I need the camera to like just follow me. Oh, they must have that. You can get one of those pet cameras or something, right? 9 and 3. Let's think about this. That would be 9. 1, 2, 3, 4, something like that. Oh, we got 3, 1, 2. Probably, yeah, there's gonna be 2 here. Can't be 2 here. So this is 2. 3 1s. Anyway, there's 10. 9, 10. It's probably 2, but not sure. Not sure. And what else can we do? We got 7 here. So 7. Wait, no. Yeah, it's difficult. If you make a mistake, you really could get messed up. Now, this has to be 2, which means the 1 has to be here. And that's 3. And 4 goes over here. There's 2 and then 2 on the column, so it can't be here. And this has to be 2 then. I messed up, it looks like. We got 1 and then 2. I messed up some more. Hold on, let's try to... Sometimes it's very hard to save it. This one's wrong, right? This is wrong. This is switched on, which now makes sense. Hopefully I saved it, but I'm not sure. Heard a noise, but you know what? I forgot to close the. Oh, I forgot to close the window. I better close the window. Be right back. Oh no, it's closed. It's closed. It's worried it. If you leave the window open, a cat could come flying into your house. That would be crazy. Cats. I mean, that would be okay if the cat is nice, but they would probably freak out, to be honest. Alright, so 4 and 2 here. What else we got? 2. It's a nautilus. Or a hermit crab, rather. It's a hermit crab, huh? What do you call that in Japanese? Yadokari? Yadokari. Shiranakatta. I didn't know that one. Yadokari. That's a hermit crab, right? Good, good. Good, good. Seven on the bottom. We can't do that yet. We've got a lot of 15. We got some 15s. Here. Five on the column. Since I filled in one of these, no. Still can't fill in anything on the bottom there. This is a 3, which means this has to be 1. And here's 9. 9 in the row, so go like this. No. Went too far. This has got to be 6. Alright, now I have some information for the bottom row. So it's 11 cells, right? 11 cells and 7. Oh, 1, 2, 3, 4, 5, 6, 7. Be like this. By argument of symmetry, it must be symmetric. We've got 3 and 4 on this row, so this has to be 4. 3 is like this. It's in superposition. What else have we got? There's gotta be a lot of stuff we can do. 3. That's a 1 on the top. 4. Beep, 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 beep. So it has to be. Wait. This confuses me, this column. This is definitely 5. This means at max. Wait, no, I'm confused. So if this were a 5 connected, then it would be dot 1 dot, and it doesn't make sense. So this cannot be connected, therefore it's 5 like this, and then that's 1 and 1. Okay. There's 7. It's got to be like 3.1.1.7, right? It has to be. Like that. We've got information on the row. The information which we will use. Six here. 5, 6. Alright, again, let's imagine this is connected, that this is 6, and it'll be dot, then it fails. So it's not connected. It means that that's like that. make an assumption, and if that assumption is proven to be impossible, then your assumption was incorrect, and you can gain information in such a manner. So this has to be 2, 1. There's a 3 in here. It's in superposition. What I call superposition. That's a 1. 3. This looks almost like a weird airship, but I don't think that's what it is. Yeah, leave it up. Information flows around in rectangular directions, and it is satisfying. 1, 1. We got a lot of 1s. Four 1s. 1, 2, 3, 4, and then 7. Wait, I could have filled this out from the beginning, huh? 11 plus 5. How many gaps? 4 gaps. Okay. The numbers add up to 11, and then you need 4 gaps. So I could have filled it in right away. Almost finished. Two, 1, 1. We're missing 1 cell up here somewhere. But I'd like to fill this out. Somehow satisfying to actually do this. 4, 2, 3, 9. Probably right here, huh? Looks like an airship, but I don't think it is. What is that? Ducks? Oh, it's birds in a nest. Okay. Ducks. Imagine if ducks had nests in the trees. Tori no Su, it's a bird's nest. Yay. Thanks for the likes, guys. We got 5 likes on the video. Great. Live stream, whatever. That's fantastic. 10 here. In the column. Okay, 2. This is a 4. So in this column, 4 and then 8. 8. There's 9 cells, so it's like this. You can fill in this. It has 1 unit of wiggle room. Wiggle room. That's good English. Wiggle room. Wiggle is to go like this. Space for wiggling. 2, 5. That's a 5. Wonder what shape this is. Can't tell yet. Why did I do this one? No. 4 here? 4. This gotta be 3, right? Yeah. This is 9 and then 2. That's 7, 8, 9. That's a 4, so that doesn't change anything. 5 here. That's a 3, so we can do that. Oh, this is a lot of information right here, because we have these ones now. Okay, 5, 4, 4, 3. No, I don't know about that. Okay. 2. We're missing 2. It can't be here. This row is finished. This is a 3 up here in the row. I think that's a 2, right? It's a 2, yeah. And 1. What is that? A laptop on his side? No. Wait, is this some kind of symbol? Is that like an Eagle Scout symbol? Shoshinsha marker. Oh, okay. In Japan, this is the mark of a beginner mark. I don't think we have that in America. Shoshinsha marker. I think you see it on cars sometimes, indicating that it's a new driver. You also have a mark for elderly drivers. Might be the same, I'm not sure. So 13 and 1, that will be filled in. Right? Yes. We got 15 here. So 12, 13. this is 6, or it's gonna be 6, and so this has to be 4. So we got some information. What about these 1s and 11s? Let me think about this. 1.1, 2, 3. This could be 1 or 3, I guess. This is a 1, 3 here. Alright, we have another 4 1s. 1, 2, 3. Okay. Has to be at least this, and then there's a 1 up here. Not sure yet which position. I think that means I can do this, right? It's gotta be. It's gotta be. This is 11. So 3, 4, 5, 6, 7, 8. I think there's gotta be a space here, right? Yeah, it's just gotta be a space here. It has to be. Yeah. What about this one? 15. It's just filled in. Wait, I don't know about that. Okay. This is definitely 2, right? 2, 1, 2, 2. Alright, what else can we say? Got the 2 here already. I think I can mark this one, but I want to be careful. I don't want to make mistakes. Astronaut planting a flag on the moon. It looks like I almost have a mullet starting to grow. Terrible. I missed the Japanese. So let's go back to Mario Land. Getsumen Chakuriku. So Getsumen is the surface of the moon. Chakuriku is landing. Landing on the surface of the moon. Getsumen Chakuriku. What is that? Golf? I think it's golf. Golf. Golf no green. Green. The golf green. The green. Wait. There's something wrong here in this row. What's going on? Well, I got lucky, I think. Because 9 and plus 2. Yeah, I got lucky. Wait. 6, 7, 8, 9. Yeah, I just got lucky, that's all. But, okay. Looking vertically. Okay, like this. Yeah. So 9 would be like this, right? plus the x's. We have some symmetry, but not complete symmetry. Oh, 13 here. Looks like a skull. I think there's a space. There's gotta be space here, yeah. 4. Thing here. 4 ones. Wait, so I think right. I misinputted. Wait, now I'm thinking it could be an upside down guitar, but I don't think so. I think it's a weird face. Getting very close. Where would we be missing? At the top, I think. That's 7. This is a Japanese fan, I think. Matsuri Uchiwa, so festival fan. Matsuri Uchiwa. So it's 10 and then 9 and 12. I think I don't know if I can add one more there, but let's just do it manually. 1 2 3 dot 1 2 3 4 5. This is correct. Yeah. 5 dot 1 2 3. Yes, that's correct. Okay. We can do the same on this one. It's 3 and 5. This is 4, so it's blocked here. In fact, we can do a lot. On that column, 2. 4, 5. 6, 7, 8. Oh, we have 10 and 1 here. 10 and 1. Okay, so 12, 3. I think that's correct. This has to be 2. And yeah, that's 5. Good. This has to be 3. It's 5, so 3. Like that. This has got to be 5. This has to be 4. It's already 7. That's good. 2. 1 2 3 dot. Six. 3, 4, 5, 6. And that can't be connected because that would make 7. So this has got to be 1, 5, 6. So this has to be 1. This is connected. 2 and then 1. Vulture? I don't know how to say that in Japanese. Condor. Condor is different from a vulture, right? Kondoru. Not sure. So 3 and 10. It's gotta be 3. And then probably what, 4 more? Wait, it's just filled in. It's filled in. Thought it would be done right there. I'm just missing a little 3 here. What else am I missing? What am I missing? Down here, huh? Ladders? I don't know. What is that? Looks like a game or something. Is this like a Japanese thing? Ladder thing for doing permutations? Amidakuji. I think this is a Japanese thing. And Japanese people don't realize that this is a Japanese thing. They think it's like an international thing. There's actually a lot of things like that. Like Maru. Japanese people think that that's international and it's not. Maru to Batsu toka. Anyway. That's a little Japanese technique. You can make permutations using ladders. It's weird and cool. Wait, 4, yeah. Ah, it's 1 here, so okay. This one might end up being a little tricky, maybe. Let's see, we got 5? 5? No. 8 is connected here. No, what? Oh, okay. Dun dun dun! First mistake I made in a long time. As in, like, 20 minutes-ish. Alright. Got a lot of 1s here. I think it's all 1s. I'm gonna gamble. Gamble. I think it's all 1s, guys. Yeah, it's good. Educated gamble. Guess, I guess. I guess it was a guess. Eight up here. 5. So we're missing some stuff kind of in the middle. Another technique is you can just triangulate, sort of like. There just has to be a 1 here, doesn't there? Right. And we got 1 here that has to match here. Just has to match. No other option. A bird flying away from a building? Oh, it's somebody diving into a pool. Okay. Alright. Toby Komi. I guess that's called Toby Komi. Diving? I don't know. Toby Komi? This one's gonna be tricky, I can tell. It's gonna be a little tricky. Although we got, yeah, it's gonna be, wait, there's, okay. It's symmetric, that's pretty key, I think. Okay, symmetric. Okay. Symmetric. Without knowing it's symmetric, or without noticing, I think it's hard. But you notice it's symmetric and we're okay. Taishōsei ga arimasu. Is this gonna be the same? Can I guarantee there's a 1 here? I'm not sure. It looks like the same pattern as above. Should I gamble? Gamble paid off. So we filled in 9, 10, 11, 11. Oh, this is, yeah, symmetry here with the 9. That's a big deal. Three. Oh, there's 3 1s on the center. I swear this is so good for your brain, probably. All 1s. So it's here or here, it's gotta be here. That makes sense. I think we're almost done. 2 here somehow. Bell? Oh no, totally not a bell. It's why shuts it? White shirt. Although it has a tie as well. Whatever. Why shuts it? Beep, beep, 15. Do we have symmetry again? 4, 1, 5, 5. Yes, it's symmetric. By the power of symmetry. Another more complicated thing is that you can have a diagonal symmetry as well. That's sort of... I haven't seen a lot of that in this game. I'd like to see that more. It excites me. Gets my math juices going. Anyway, so these are finished through here. Okay. Maybe I'll just do that. Takes 2 seconds. And here, yada yada. Okay, cool beans. Cool beans. No, we can't figure out these yet. Looking at the columns now. This is fine. And it will be symmetric. Okay, what else can we say? What else can we do? 1 and 9 here, so I think this is connected and it's probably, looks like it's gonna make, how many is that? 8? It's gotta be like that. It's gotta be. These are 2s. We have a 1. I think it's just based on shape of how these things go. I think it's gotta be like that. And probably these are legs. Okay, so the bottom is done. 3s here. And we have a 1 somewhere in here. Okay. What else can we work on? We've got some information here. Oh, there. Okay, so weightlifter, deadlift. Is that called a deadlift? I'm not sure. What else? Okay, we know the 4. Okay, I think we're done. We just have to make it symmetric. Yeah. Weightlifter. What is this? Juryo-age? Juryo-age. So, I don't know what that's called. Is it a deadlift? I think it's a deadlift. Juryo-age? Not totally sure. 2, 3, 4. Good. Beep, beep, beep. 1, 2, 3, 4, 5, 6. I think that's correct. Can't. ちょうど何もできないここ. I don't know how to say it in English. Somebody speaking English a Japanese person speaking English incorrectly would say, "We just can't do it." But they use just incorrectly. But yeah, we just barely cannot do anything on this row. Anyway, but that English is still a little weird. We just barely can't. That's weird. I don't know how to say it. ちょうど何もできない。まあ私の日本語もおかしいかもしれないけど、わかんないです。自分の日本語がおかしかったら、なんかそれはわからないときありますよね。狂ってる人が自分はおかしいと思ってないと一緒。You don't know. Crazy people don't know they're crazy, but that's not always true. That's sort of a myth, right? Sometimes it's true. 3, 4. This has to be 4. This has to be 1, I think. Nah, you could have 1 and then 3. What else can we do? 3 up here. Okay, good. Progress. That's a 3, but it doesn't really help. You know, I don't know. So this is definitely 3, so we can fill this in. And that's a 3, vertically. Good, yay. We have 4 here. Information just flows. These are all 1s on this row. Looks like a mouse. Five here, so... Ah, misclick. Okay, this is good. This is, no, this is finished. 611. Got that already. This also serves to check that you didn't make a mistake sometimes. We're missing a 1, so it has to be here. That's probably the end. Yeah. Is it a... what is that? A deer? Yeah. Shika. That's a deer. Huh? Kojika? Is that a male deer? Oh no, it's a baby deer, I think. Kojika, maybe. Maybe. This one might be symmetric. No. On the wings we have asymmetry. Okay, which there's a lot more on this left side. Okay. Do this one as well, huh? That's a 5. Probably it's this one, but I won't jump to conclusions just yet. Not until I have proof. This 4. can't. I'm gonna pretend I didn't do that. I meant to go here. 2. Oh, it's spectacles. I like it when there's almost symmetry, but not quite. Gets my brain flowing. My brain juices. Because one day I'd like to be able to see, to look at the numbers that you start with, see that the symmetry is slightly off in some place, and then to be able to see the whole image without filling it in. Like if there's a lot of symmetry, you might be able to do that. That's the dream. One day, to be able to see the image without like working it out. That would be crazy. But I think these problems are NP hard, which means that... Are they NP hard? I think they're NP hard. Wait. I don't... Never mind. I'm not sure about that. Probably not, right? I mean, you can make some where... You can make one where the solution is not guaranteed, actually. Is this already 11? And then boom. Okay, I'm gonna use the bathroom real quick. We've been streaming 5 hours? Holy bananas. How many views we got on this so far? How many views we got on this? I don't know. Chrome is stuck in guest mode. I don't know how to get out of it. New window, but when I make a new window, it's still in guest mode. Whatever. I'm gonna the restroom. What should we do? I'm stuck in guest mode. Whatever. Let's check things on the phone. Alright. Almost 600 views on this. That's good. I think I might need to stop though. I need to eat food. Alright, everybody, thank you. Thanks for the likes and the subs. Very helpful. Hope you have a great rest of the day. I'm gonna sign off. Thanks. Bye-bye.